Chapter 12, Chemical Kinetics. Our outline is Introduction, Reaction Rates, Differential Rate Laws, Integrated Rate Laws, and Half-Lives, Reaction Mechanisms, Collision Model, and Catalysts. Introduction. In Chemistry 1, we acted like all reactions went completely to products, and that they did so quickly. Not all reactions are quick, and not all reactions go completely to products. In this chapter, we'll study the factors that affect the speed with which reactions occur. This topic is called chemical kinetics. Chemical kinetics is the study of reaction rates. In the following 4 chapters, we'll discuss what to do when a reaction doesn't go all the way to products. We're familiar with combining an acid and a base and getting a reaction that occurs immediately. If we have a thermometer in the mixture, or if we simply feel the beaker where the reaction was done, we feel it's warm. The thermometer temperature has gone up. It's an immediate reaction. Other reactions are not immediate. Here's a reaction involving iron 3+ and S2O3 2-. That reaction is not a quick one. In that reaction, the Fe3+ has an orange color, and the Fe2+ has a pale green color. The sulfur compounds are colorless. Well, when we combine the reactants, Fe3+ and the S2O3 2-, we see an immediate change in the color from orange to violet, not pale green. Slowly, the violet color becomes a pale green, but it turns out it doesn't go completely to pale green. When we probe that reaction more, we find that it looks like one Fe3+ combines with the two S2O3 2- to give us this intermediate, as we call it, which is Fe S2O3 2-. That's what has the violet color. That is step 1 of this overall reaction, and that occurs very quickly. That's what we call the fast step. Slowly, the Fe S2O3 2- combines with the other Fe3+ to give us 2 Fe2+ plus S4O6 2-. And that is the second step. That is the slow step. Step 1 and step 2 are what we call the mechanism of this overall reaction. It doesn't go all the way to products, as it turns out, and that's a topic we deal with in those next 4 chapters. When copper 2+ is added, it acts as a catalyst and speeds up the second step, the slow step, and the color fades much more rapidly. So the catalyst can speed up the reaction by interacting in such a way with the slow step of the mechanism to make it go faster. It does not become more pale green, however. A catalyst only speeds up a reaction. Our next section is reaction rates. In general, rate is change in property over time. We're familiar with speed. We think about that as we drive our car. And speed would be the change in distance over the time it takes for that change. We often indicate change with the symbol delta. Delta would be the initial quantity, the final quantity minus the initial quantity. So in speed, it would be the final distance minus, or the final location minus the initial location, the difference being the distance. Well, since we're talking about chemical kinetics with respect to this rate, we have reaction rate, and that is the change in concentration over time. Let's say that we have a reactant A, some chemical A, forming products. The rate, the reaction rate, is the change in the concentration of A over the time it takes for that to occur. We use brackets, square brackets, around our chemical to represent its concentration, usually in units of molarity. Here's some data, and we will work with it in calculating some rates of reaction. Our reaction is 2N2O5 forming 4NO2 plus O2. Our temperature is 25 degrees Celsius. It turns out reaction rates are very dependent on temperature. All of our reactants and products are gases. So we have data that begins at, of course, time 0, and we monitor reaction concentrations for 700 seconds. Our first column is, you see, time in seconds. Our second column is the concentration of the reactant, N2O5 moles per liter. And the third and fourth columns are concentrations of the products, the NO2 and the O2. Something to note about our reaction is the stoichiometric coefficients, 2 N2O5 forming 4 NO2 plus 1 O2. So if we start with 0.02 molar N2O5 and monitor its concentration and the concentrations of the products and make a graph from the data, we get this graph here, which is concentration versus time for our reaction. We see concentration on the y-axis, moles per liter, time on the x-axis in seconds. And without looking at the key, let's just make sure we make sense of everything. The products must be the ones whose concentrations are increasing over time, and the reactant must be the one whose concentration is decreasing. So that would mean the blue represents the N2O5, and the red and the green, the products. Of those two, we see that our mole ratios between the two are 4:1. So we get 4 times the amount of NO2 as O2 over any given time period. So that means that the NO2 is the red one and the O2 is represented by the green line. So we see nothing is linear, how they decrease, how they increase. We'll make some calculations now of rates of the reaction. So our problem is calculate the average rate of decomposition of N2O5, of formation of NO2, and of formation of O2, all at 50 seconds. And what we're going to do is use the data between the 0 and 100 seconds, the concentration data and the time data. So first we are after the rate of the decomposition of the reactant. So what we have to do is quickly go back to our table and note the concentration at 100 seconds, 0.0169 molar, and at 0 seconds, 0.02, and pretend that has zeros on the end. In Excel, which is what I use to prepare it, it drops the zeros that are after the last digit. Okay, so we have those values. So Our rate is going to be the final concentration 0.0169 minus the initial 0.0200 moles per liter, dividing by the time, 100 seconds. We get the rate of the N2O5 to be 3.1 times 10 to the minus 5. Notice the units are moles per liter second. Nothing cancels out. We've got all those units. In fact, rate units are, if we are working with concentration in molarity and time in seconds, come out to be moles per liter seconds. Notice that although we're taking a smaller number and subtracting a bigger one, we drop the negative sign because we know that the concentration is decreasing, so the rate would be negative, but it's easier not to carry that negative sign. The rate of formation of the NO2, that would be the concentration at 100 seconds minus the initial. So we have 0.0063 minus 0 moles per liter divided by the 100 seconds. We get 6.3 times 10 to the minus 5 moles per liter seconds. And then for the O2, we do a similar calculation. 0.0016 minus 0 divided by 100, we get its rate to be 1.6 times 10 to the minus 5 moles per liter seconds. Now notice that the rate of the N2O5 is about half the rate of the NO2. That's got to do with those stoichiometric coefficients. Remember, it was 2 N2O5 forming 4 NO2 plus 1 O2. So the ratios are reflected in these rates. The rate of the NO2 versus the rate of the O2, it's about 4 to 1. We could predict, if that is to say, if we have the rate of the N2O5 being this 3.1 times 10 to the minus 5 moles per liter second, and we want to calculate from it the rate, for example, of the O2, then we could do it as we see here, predictable from stoichiometric coefficients. We put the rate of the one we have, we put the mole ratio between the ones we're going from and to, so we have the 4 moles of NO2 over 2 moles of N2O5. Notice the moles of the N2O5 cancels out, and we are multiplying by 2, and we get the 6.2 times 10 to the minus 5 moles per liter second, which is about the 6.3 times 10 to the minus 5 that we calculated from the data. These are average rates. Notice we went between 0 and 100 seconds, and we were saying, well, that's the rate, about the rate at 50 seconds. It turns out it's a little different if we determine the rate at exactly 50 seconds. For the accurate rate at exactly 50 seconds, what we have to do is draw a line, a tangent to the curve at 50 seconds and calculate the slope of that line. Remember that rates are concentration divided by time. And we have on our graph here concentration on the y-axis, time on the x-axis. Rate is the change in concentration over the change in time. So that's going to be the slope. Okay, so we are going to calculate the accurate rate for the decomposition of N2O5 right at 50 seconds. And what we do is we go back to our graph of concentration versus time, and we draw, just get out a straight edge, do the best you can to draw a line right at 50 seconds. And so I've done that by just drawing a pencil line there. So I saw where 50 is, of course, halfway between 0 and 100 seconds. And I put my ruler right at the blue line. going with the shape of it that I could best predict at 50 seconds and drew that slope line. Now what we have to do is determine the slope of that line. So that's the rise, concentration change, divided by the run, the time change. So we have delta y over delta x. And looking at the values I saw on the graph, I did the 0.02 minus 0 for the concentration change, divided by 660 minus 0 for the time change, and got the rate at N2O at the 50 seconds to be 3.0 times 10 to the minus 5. The units would be the units for the y-axis divided by the units of the x-axis, moles per liter, divided by seconds. So we have the same moles per liter seconds. And this is very close to the average rate, but not exactly. Notice that if we were to draw a tangent at various locations as time goes on for the blue line, we would see that the tangent is the steepest at first, and then it gets less as we go. That is to say, the rate is the fastest when we first put our reactant in our container and start it, because we have most of it present then. As it gets used up, there's less of it to react, and the rate slows down. Okay, our next section is the differential rate laws, which are often referred to simply as the rate laws. That's why I put differential in parentheses. So now we will focus on rate at certain concentrations rather than at certain times. Rates of most reactions depend on the concentration of the reactants. So let's say we have AA forming BB. That is to say, little a, little b, those are stoichiometric coefficients, and the A, the big B are some chemicals. Often as the concentration of A increases, the rate increases. Experimental data shows that rate is equal to K times the concentration of A to a power N, where N for our purposes will be either 0 or 1 or 2. If you go on in chemistry, you will see that there are more possible values for N. Note, this is very important, N is determined from experiment, not from the balanced reaction. We can't look at the little a and the little b's or something like that, the stoichiometric coefficients, to determine what N is. N comes from experiment. K is what we call the rate constant. It depends upon temperature. So the rate of the reaction is temperature dependent, and that shows up in K, the rate constant. K is not rate, it is the rate constant. The rate is K multiplied by A to the N. In the table there, we see the 3 possible values that N can take on, and what we call that kind of a reaction we refer to, when we're talking chemical kinetics, a zero order reaction as one where N is 0. When N is 1, we call that a first order reaction. When N is 2, a second order reaction. So when we have rate equals Ka to the N and N is 0, we have A to the 0, anything to the 0 is 1. So the rate for a zero order reaction is simply K. And a graph of rate versus concentration would simply give a horizontal line, since the rate is constant. And it would give a horizontal line whose value would be whatever K's value is. That would be the case for a zero order reaction. A first order reaction, there we have n equals 1, so we have rate equals Ka to the 1, or simply Ka, and a graph of rate versus A gives a linear curve, gives a straight line with a slope equal to K. Notice if you think of y equals mx plus b, where the y-intercept here is 0, so b is 0, we have rate y, mk, the slope, and a x, so the slope is k. For a second order reaction, we have rate equals Ka squared, and a graph of rate versus A gives a quadratic curve, gives a curved curve. And if we wanted a linear graph, we would have to make a graph of rate versus A squared. Using new N2O5 data, same reaction but new data, we will determine if the reaction is 0, first or second order. So here's our reaction, 2 N2O5 yielding 4 NO2 plus O2. And we want to know, is it first order, second order, or 0 order? So if it's 0 order, then the rate is constant. That is to say, we'd get that horizontal line. If it's first order, then rate versus N2O5 gives us a linear graph. If it's second order, rate versus N2O5 squared gives a linear graph. Okay, so here's our data. We have time 0 up to 1800 seconds, and we have our N2O5 concentrations in units of moles per liter. Now, what we would do is make a graph of the N2O5 versus time, and it looks like this. It's got that bent shape to it. Now, what we would do in order to determine the rates, we would do it as we did for that accurate rates method. We would draw tangents at lots of points along our curve. We would determine the slopes of all of those tangents. And that's what I did. I actually used Excel to do that. So our third column in this table is the slopes at those different times. The slope is negative. Now, in that fourth column, what I did was I simply dropped the negative sign and went from the ordinary notation to scientific notation. So negative 0.00057, if I drop the negative sign and go to scientific notation, we have 5.70 times 10 to the minus 4. So we have then rate at different times, which we're going to make a graph of. We're also going to make a graph of rate, those same rates, versus concentration of N2O5 squared, so that we can compare. We'll make a graph to look at first order, we'll make a graph to look at second order. We know it's not 0 order because we see that the rate of the N2O5 over time changes, so it cannot be 0 order. Alrighty, so we know it's not 0 order because the rate's not constant. So now we'll check if it's first order by making that looking at the rate versus N2O5, and we'll check if second order by looking at rate versus N2O5 squared. Whichever gives better linear data is going to indicate which one it is. Alrighty, so here is then rate versus N2O5, and what I did was I plotted the data in Excel, and then I had it do a linear fit and give a correlation coefficient. That's shown at the bottom part of the graph as r squared equals 0.99049. The closer is that number to 1, the closer is the data to the linear fit. So the linear fit revealed a slope of 0.00057 and a y-intercept of 2 times 10 to the minus 5, which is almost 0. Okay, so we have a correlation coefficient very close to 1, making the data look pretty first order. But we'll check if second order doing the same kind of thing. So there's the graph of rate versus concentration squared. And I did the linear fit and got the slope to be 0.0004, the y-intercept 0.0002, got the correlation coefficient to be 0.95393, not as good as the correlation coefficient for the first order fit. So rate versus the N2O5 concentration fits well to a linear function with a correlation of 0.99. I dropped the last digits. The slope of the fit is 5.7 times 10 to the minus 4, and the units are 1 over second. So notice up here that the slope has the units of the y-axis units, moles per liter second, divided by the x-axis units, moles per liter. So the moles per liter cancels out, leaving us with just 1 over seconds. And I took the value, that 0.00057, and just converted it into scientific notation. Alrighty, so we have the slope, 5.7 times 10 to the minus 4, 1 over seconds. The rate versus N2O5 squared does not fit as well. The correlation coefficient is less. So we conclude that the N2O5 decomposition reaction is first order, at least at that temperature where we have the data. So what we have is rate equals K times N2O5, and K is the slope, which is 5.7 times 10 to the minus 4, 1 over second. So our equation is rate equals 5.7 times 10 to the minus 4 times N2O5. And since we know the rate equation, we can calculate the rate at different concentrations, of course, at our same temperature. Rate is very temperature dependent. As we go to higher temperature, the rate constant value actually goes up and we have higher rates. Okay, so let's calculate the rate at the N2O5 concentration of 0.050 moles per liter. So we take our rate equation, 5.7 times 10 to the minus 4, and multiply it by the concentration, 0.050, and we then calculate the rate to be 2.9 times 10 to the minus 5 with our units moles per liter seconds. Alrighty, so now we're going to do the same kind of thing but with a new reaction and new data. Our reaction is 2C4H6 forming C8H12. Temperature is 500 degrees Kelvin. We have data, and we have the time data. We have the C4H6 data. And then what I did was I made a graph, concentration versus time. And by the way, the table on the left there of the graph is covering the label for the y-axis. The y-axis label is the concentration of the C4H6 in moles per liter units. And so I did the fitting at many different time values and got the slopes. Then we have our fourth column, which is the rate of the C4H6 moles per liter seconds, just the slopes where I dropped the negative sign. I also have a column of the concentration of the C4H6 squared. Okay, and then so we know in order to determine if zero order or first or second, we know not zero order because the rate is not constant, it varies. So we will check if first order by making a graph of rate versus C4H6. We will check if second order, making a graph of rate versus C4H6 squared. So here is rate versus C4H6. As before, I fit it with a linear function, got a correlation coefficient of 0.90444. I made a graph of rate versus C4H6 squared, did the linear fit and got a value for the correlation coefficient of 0.95609. That is better than the correlation coefficient for the first order situation. So that would imply that it is, we go with the better of the two on the correlation coefficient being closest to 1. So it would imply that it's second order. Notice that from our linear fit, we have a slope of 0.0072. We have a y-intercept of 8 times 10 to the minus 7, which is almost 0. We will call it 0. Alrighty, so we have the rate versus C4H6 squared fitting fairly well to a linear function. The correlation is 0.96 and the slope is 0.0072. The units come out this time to be liters per mole seconds because we have on the y-axis moles per liter seconds, on the x-axis moles squared per liter squared. So run through that and you will see that the units come out for the slope to be liters per mole seconds. And we're not calling it a first order reaction because the correlation coefficient is not as good. From this, we conclude that the C4H6 reaction is second order. So we have rate equals K times C4H6 squared, and K, which is the slope, is 0.0072 liters per mole second, giving us rate equals 0.0072 times C4H6 concentration squared. Now we can make a calculation where we calculate the rate of C4H6 at the concentration 0.0080 moles per liter, and we would get the rate to be then 5.8 times 10 to the minus 5. Notice that, of course, we are following the equation rate equals 0.0072 times concentration squared. So we're squaring the concentration. And units work out to be our usual rate units, moles per liter seconds. We're going to do one more such example, this time working with the reaction 2NH3 yielding N2 plus 3H2. And I have data, but I'm not sure at what temperature. So here's our time data in seconds, our concentration of the NH3 in moles per liter. So I made the graph. I determined the slope at different times, and the slope came out to always be negative 0.0025. That is to say, the rate for the NH3 in units of moles per liter second is 0.0025. So what we have is a zero order reaction because the rate is constant. So we have our graph of rate versus concentration. It's horizontal the slope, the value of that line is 0.0025. So what we have is a zero order reaction. And rate is K, which is 0.0025. The units are moles per liter seconds because if we look at our graph here, it's just the value of Y, which is moles per liter seconds. So if we wanted to make some sort of a calculation of rate at a different concentration, let's say a value of 1.75 moles per liter, well, concentration doesn't fit into our equation. Our equation is simply rate is that number, 0.0025 with units of moles per liter seconds. So that's our rate at all those different, whatever the different concentrations would be, provided it's at that temperature. What is a zero order reaction? They are kind of unusual. So they come up usually when we are using a solid catalyst. Remember, a catalyst speeds up a reaction. And when we have a solid catalyst that reactants go on to, and it makes them kind of cling to it, and it helps to break bonds between reactant atoms, then that often gives rise to a zero order reaction. And we have that here when we combine H2 with H2C, CH2, which is called ethylene or ethene. So what's happening there is that the H2 is breaking, and each one of those H atoms is adding on to one of the carbons of the other reactant, breaking that pi bond. Think of the octet rule, carbon only once, an octet. And it forms the product H3CCH3, which is ethane. So the reactant's pi bond is fairly easy to break. Pi bonds are kind of sticking out. Remember, they're bonding above and below the axis, the internuclear axis, and they're somewhat easy to break. But the H2 bond, being a sigma bond, is harder to break. So that reaction, without the presence of the catalyst, which is a piece of platinum that's represented in the diagram by the gold atoms, the gold balls, what happens is the H2 and the ethylene are put into a reaction flask where the catalyst is, the platinum piece is, and they collect on it, and that interaction between the H atoms and the platinum atoms just weakens that HH sigma bond. And the hydrogen atoms then come apart. Now they're individual atoms, and they can each migrate to ethylene and add on to it, giving our product, the C2H6 product. Here's another zero order reaction so that we can get a sense of this concentration, the lack of concentration dependence. So our reaction here is 2N2O gas forming 2N2 gas plus O2 gas. The N2O is represented in the diagram by the molecule that has the two blue N atoms and the one red O atom. So if we put just a little bit of the N2O into the reaction chamber with the platinum surface, then it adheres to it, that weakens bonds, and that allows it then to react. Now, once the platinum surface is saturated, it doesn't matter if we add more N2O. The reaction will not go any quicker. So it's really dependent upon basically how big the platinum is. In that sense, it's not dependent on the concentration of the N2O, making it a first order reaction. I'm sorry, making it a zero order reaction. Here's a summary table of the information that we have worked with so far. So we have AA forming products, big A of course being the chemical. So for a first order reaction, the differential rate law is rate equals Ka. So a graph of rate versus time gives us a linear graph. For a second order reaction, we have rate equals Ka squared. So to get a linear graph, what we have to do is plot rate versus concentration squared. And for a zero order reaction, we have rate equals K. So rate versus concentration gives simply a horizontal line at the value K. Another way to determine the rate of a reaction is what's called the initial rates method. And we will work with this method, working with this value, with this reaction BrO3 minus plus 5Br minus plus 6H plus yielding 3Br2 plus 3H2O. And we're going to find the rate law of that reaction as well as the value of K given the data that we have in the table. So the rate law conceivably depends upon the concentration of BrO3 minus, Br minus, and H plus. So we have rate equals K times BrO3 minus to the power M times Br minus to the power N times H plus to the power P, where those powers M, N, and P are the orders. I had to use 3 different symbols because we have 3 different possibilities. So we will determine the value of the orders M, N, and P, and the value of K, the rate constant. So we have the data here for 4 different experiments done using that reaction. What's different about each experiment is the concentrations of the reactants. And we are also given the rates of the reaction when those initial concentrations were first put into a reaction flask. Of course, it took a lot of time to come up with all those rates and so forth, but anyway, we've got them all here to work with. So we will first determine the values of M, N, and P, and then we will determine the value of K. Now notice that as we scan the concentrations at the various experiments, often the concentrations are 0.10. Sometimes they're changed to 0.2, 0.3. They're often the same value so that we can cancel them out and make our math here easier. So what we're going to do is take the rates, write out the rate law and put in concentrations for experiment 1, and then we will do the same for experiment 2, and we will divide those rate laws by each other, and we'll see that a lot of stuff cancels out. So basically we look for experiments where all but one ion's concentrations are constant. So rate 1, 0.0012 divided by rate 2, 0.0024 equals, in the top, K times 0.10 to the M times 0.10 to the N times 0.10 to the P. And then we have in the bottom, for the second experiment, K times 0.20 to the M times 0.10 to the N times 0.10 to the P. notice that 0.10 to the n over 0.10 to the n is equal to 0.10 divided by 0.10 to the n, which is 1 to the n, which is simply 1. So the n stuff cancels out. By the same reasoning, the p stuff cancels out. Also, we have k over k. That cancels out. So what we end up with is just one unknown, and that is m. We have 0.0012 divided by 0.0024, which comes out to be 1/2. That equals 0.10 to the m over 0.20 to the m, which is equal to 0.10 over 0.20 all to the m, which is equal to 1/2 to the m. So we have 1/2 equals 1/2 to the m. We conclude that m is 1. Now we look for data we'll next determine the value of n. So what we do is we look for data where only the Br minus concentration changes, and the BrO3 and the H plus concentrations are constant. So we'll take experiment 1 and experiment 3 data. Alrighty, so taking that data, we write out rate 1 over rate 3, and we put all of our numbers in. We see that a lot of stuff cancels out, and we are left with 1/3 equals 0.10 to the n over 0.30 to the n, which is 1/3 equals 1/3 to the n. We have n equals 1. Lastly, we work with the p data, the H plus data. So we do the same thing. We find where only the H plus concentration is changing, and that occurs in rates for experiments 2 and 4. So we write out our rate 2 over rate 4 with all the numbers. Lots of stuff cancels out. We end up with 1/4 equals 1/2 to the p, and that would imply that p is 2. So that allowed us then to write out rate equals k times BrO3 minus times Br minus times H plus squared. So we have gone through this example quickly. Definitely go back looking at the handout and run through this one yourself. Okay, now we're ready to determine the value of k. So what we do is we take our rate law and we solve for k. So k equals rate divided by BrO3 minus divided by Br minus divided by H plus squared. And from our data, we take one of the experiments. I took the experiment 1 data, and we write the rate 0.0012 moles per liter second, and the concentrations in the bottom. We have 0.10 moles per liter, 0.10 moles per liter, 0.10 moles per liter squared, and the division gives us the value 12 and gives us the value liters cubed over moles cubed seconds. So definitely come back and go through this example and make sure that numbers, units, everything works out. So what we finally have is rate equals 12 times BrO3 minus times Br minus times H plus squared. We would say our reaction is first order with respect to the BrO3 minus, and first order with respect to the Br minus, and second order with respect to the H plus. We could call it fourth order overall. Okay, our next section is integrated rate laws and half-lives. Let's say we want the concentration of A during the course of a reaction. For a first order reaction, we have learned that rate equals Ka. Well, Some of you are in calculus, so you have a sense of going from a differential equation to, by integration, to not a differential equation anymore. But that isn't a requirement for this class, so you just have to go with me when I say that a first order reaction has the differential equation, the differential rate law equation being rate equals Ka. The integrated rate law is A equals A naught e to the minus Kt. So depending on what we want, if we want rate, we're thinking of the differential rate law. If we want concentration versus time, we think of the integrated rate law. That is to say, rate equals Ka goes along with A equals A naught e to the minus Kt. One is the rate law that's the differential form. One is the rate law that's what we call the integrated rate form. So what we have is A versus time being an exponential sort of function. Now, that A equals A naught e to the minus Kt, what all that means is A, its concentration as a function of time, t. K in that expression is that same K from before, the rate law, the rate constant. And A naught is the initial concentration of A. We often use a symbol 0, naught, we call it, to represent initial. Sometimes you'll see a small case I to represent initial. So in our graph, we see that the initial concentration of A is about 1, and we see how it decreases then with time. If we wanted a linear version of this equation, well, we would take the log of each side, the natural log, because we're working with the log to the base e, not the base 10. So we have, if we take the ln of both sides, what we get is ln of A equals ln of A naught minus Kt. If we equate that with y equals mx plus b, we would have y equals b plus mx written directly below. That is to say, ln of A like y, and then ln of A naught is the y-intercept, b, and then we have minus kt equated with mx, that is m is minus k, and x would be like time. Okay, so a graph of ln of A versus time is linear with a slope of minus k. Okay, now we'll think about half-life. So half-life is the time it takes for the material to drop to half its original amount. You may have heard of half-lives in connection with radioactivity. The half-life of uranium is a certain value, a certain time period. It takes that much time for the mass of the uranium to drop to half that original amount. You may have also heard of that in connection with medicines. People sometimes have a medical test done where they're given a certain compound, and the compound in their body is investigated to see like where it goes and what it clings on to. That could be following maybe a cancerous cells, something like that. So the half-life of the chemical that they are given is a reflection of how soon the person can think that chemical is mostly out of their body. Often it's given such that when 3 half-lives of the chemical have passed, then the chemical is pretty much gone from the person's body. Alrighty, so the half-life is the time it takes for the material to drop to half its original amount. So we see A naught on our graph. There's our graph A versus time. A naught is that initial amount, the value 1. When it drops to half that, which would be 0.5, the time it takes for that to occur would be the half-life. So we see it's somewhere around 8, whatever the time units are. To find the half-life for a first-order reaction, we're going to see that we can derive that from our integrated rate law. So we're going to take the linear version of it, ln of A equals ln of A naught minus kt. What we're after is solving for time. So with some algebra, we have kt equals ln of A naught minus ln of A. We can combine those two terms. Ln of A naught minus ln of A is equal to ln of the ratio A naught over A. Now, the half-life is the time it takes for A to be 1/2 A naught. So for A, I put in 1/2 A naught. So now we have K times the half-life equals ln of A naught over 1/2 A naught. Well, the A naughts cancel out, and we get kt is equal to ln of 2. Solving for the half-life, we have t equals ln of 2 over k. The ln of 2 is 0.693. It goes on, but those are the first 3 digits of ln of 2. So that's our half-life equation for a first-order reaction. T equals ln of 2, or 0.693 over k. Notice that the A naught stuff all canceled out. The half-life for a first-order reaction is independent of A naught. And so a graph of concentration versus time we have here for a chemical that we had talked about earlier, N2O5. And if we start with the initial amount of 0.10, then the half-life is the time it takes for it to drop to 0.0500. And following our graph, we go down to that, and the time is 100. So we would conclude the half-life of N2O5 is 100 seconds. And because the half-life for a first-order reaction and the N2O5 data gives us, as we concluded earlier, first-order reaction, the second half-life is just twice that value. The third half-life would be 3 times that value. Okay, so now we have some examples to work with. So what we have is the integrated rate law for a first-order reaction. We know what it looks like. We know what the half-life equation looks like. Those have all been for just the first-order type reaction. In a moment, we're going to deal with the second-order type reaction and its integrated rate law, its half-life, and then we will deal with a zero-order reaction, its integrated rate law, and its half-life. But we're dealing right now with a first-order reaction. So in our problem here, we have a first-order reaction, and we have that its rate constant, K, is 0.0693 1/seconds. So what is the first half-life of the reaction? What is the second half-life? The first half-life is what we often term simply the half-life. Okay, so the half-life, that is, we have a first-order reaction, so that's time equals 0.693 over K. We put in our value of K. It turns out to be 0.0693 1/seconds. So we end up with the half-life to be 10.0 seconds. Well, the half-life, since we're dealing with a first-order reaction, is simply twice that value, so 20 seconds, 20.0 seconds. Here's a new problem. It's also a first-order reaction. So a first order reaction is 40% complete in 410 seconds. So it's 40% complete. That means 60% of it is still, you might say, unreacted. It's 60% left to go. Our first part of the problem is, what is the value of K? So we have that at time t equals 410 seconds, the concentration of A at that time is 0.60 A naught. And that goes back to what I said a moment ago. For a reaction to be 40% complete, 60% is still yet to react. So A at that time of 410 seconds is 0.60 times whatever it was originally. Okay, so for a first order reaction, we have ln of A equals ln of A naught minus KT, which we can rearrange to KT equals ln of A naught over A. Dividing by time, we get K equals 1 over T ln of A naught over A. Putting in our numbers, K equals 1 over 410 seconds times ln of A naught over 0.60 A naught. Notice we never did learn the original concentration, but it turns out it cancels out, so it did not matter. So A naught cancels out, so we have 1 over 410 times the log of 1 over 0.6, which comes out to be K equals 0.00125 1 over seconds. Rounded to 2 sig figs, we have K equals 0.0013 1 over second. So that would be the value of the rate constant. What are the first and second half-lives? So the half-life equation, time equals 0.693 over K. 0.693 over 0.00125 1 over seconds. Notice I take the more the value of K with more digits, because you might say I'm midway through a calculation here. So I go back to that 0.00125 as opposed to the more rounded one, 0.0013, and I get time equals 560 seconds. The second half-life is twice that, or 110 seconds. Alrighty, so the same kind of problem, the first order reaction problem, how long does it take for 90% completion? So that means 10% is yet to go. So come back and do that problem. Okay, so as I said before, we developed the integrated rate law and the half-life for a first order reaction. Now we will do the same thing for a second order reaction. A second order reaction, the differential rate law is rate equals Ka squared. Again, calculus can show that that becomes, when we want A versus time, it becomes 1 over A equals 1 over A naught plus KT. So a graph of 1 over A versus time gives a linear function with a slope of K and a y-intercept of 1 over A naught, as is shown below here. Alrighty, so now the half-life equation, so we take our integrated, second order integrated rate law, 1 over A equals 1 over A naught plus KT. Solve for time, time equals 1 over k times 1 over a minus 1 over a naught. And then for a, we put in 1/2 a naught in order to solve for the t sub 1/2 equation. So we have 1 over k times the quantity 1 over 1/2 a naught minus 1 over a naught. And that becomes 1 over k equals 2 over a naught minus 1 over a naught. T equals 1 over k times 1 over a naught. And that's our half-life equation. So for a second order reaction, the half-life is T equals 1 over k a naught. Notice that the half-life depends not only on k, but also on a naught. It is not constant as the reaction proceeds. As a naught decreases, T sub 1/2 increases. The reaction goes slower. Okay, so that's all the info for a second order reaction. We have the integrated rate law, we have the half-life equation. For a zero order reaction, we'll do the same things. We'll come up with the integrated rate law and the half-life equation. So for a zero order reaction, rate equals k. Calculus shows that A equals A naught minus KT. That would be our integrated rate law for a zero order reaction. So A versus time, we get a linear function where the slope is negative k and the y-intercept is a naught. Alrighty, to get the half-life equation, we take our integrated rate law, A equals a naught minus kt. Solving for time, we get time equals 1 over k times a naught minus a. We put in for a 1/2 a naught, and we run through the algebra, and we get that the half-life equation for a zero order reaction is a naught over 2k. Notice that the half-life depends not only on k, but also on a naught. It's not constant as the reaction proceeds. As a naught decreases, T sub 1/2 decreases. The reaction goes faster. Alrighty, so now we have a summary of all of this in this table. For a first order reaction, we know from early on in this chapter, the rate equals Ka. And the integrated rate law is ln of A equals ln of A naught minus Kt, or we could write that as A equals A naught e to the minus Kt. So the linear graph, we would use the ln form, and we would have ln of A versus time. And the slope is negative k. The half-life equation for a first order reaction is T sub 1/2 equals 0.693 over k. For a second order reaction, the differential rate law is rate equals Ka squared. And our integrated rate law is 1 over A equals 1 over A naught plus Kt. So a graph of 1 over A versus time is linear with a slope of k. The half-life equation is T sub 1/2 equals 1 over k A naught. For a zero order reaction, rate equals k. Our integrated rate law is A equals A naught minus Kt. So A versus time gives a linear function with a slope of minus k. The half-life equation is T sub 1/2 equals A naught over 2k. Our next section is reaction mechanism. The reaction mechanism is a series of steps by which a reaction occurs. These steps are called elementary steps, and they show exactly how the reactants in each step actually react. An elementary step is a reaction whose rate law can be written from it. Okay, so let's say we have an overall reaction being 2A forms B. Of course, A and B are chemicals. So 2A forms B. And let's say that the the steps that give rise to this overall reaction are A forming C, where C is some kind of an intermediate, and then that C, that intermediate, reacts with the other A to give B, our product. So those are two steps. They are what we call elementary steps. And what they mean is, in our first elementary step, A directly forms C. A just reacts to become C. Our second step is telling us that C reacts directly with another A to give B. And the rate law for this overall reaction to A forming B would be written from the slower of these two elementary steps. Whichever is the slower of the two is going to basically be the rate limiter. It's going to be the rate determiner of the overall rate of the reaction. So one of those two steps is slower, and it's going to be the one that determines the rate. We will come back to the reaction mechanism in a moment. So here's our overall reaction, 2A forming B. Our mechanism, our steps are A forming C, and then C plus A forming B. If the first step is the slow step, what is the rate law? Well, if that determines the speed at which the reaction can go, it's what we call the slow step. It gives us the rate. Now, we read it directly. We see that A doesn't have to combine with something else. It just simply becomes C. So that means it's first order with respect to A. We would say the rate of that overall reaction must be rate equals Ka. And then that would have to be supported by an experiment that shows from all of the data that in fact the reaction is first order overall. So what we do is we, as chemists, we have a reaction and let's say that it's we want it to go faster. We're some sort of an industrial chemist. We want to make more product using a particular reaction. We want to make it, I don't mean to say more product, we want to make it occur faster. We want to get the product quicker. So we want to speed up the reaction. So what we would do is go to the lab and we would determine what is the order of this reaction, just as we've done with the data we looked at earlier in this chapter. And we would determine, let's say it's a first order reaction. So then we would write out a possible mechanism. What might be occurring? What are the elementary steps? And we would have to make sure that our elementary step that we thought is the slow one is consistent with the order. If it's a first order reaction, then it has to be that that slow step in our mechanism is simply rate equals Ka. And then we would find a way to speed up that slow step. So going back to the reaction mechanism requirements, what's at the top of this screen, we have the reaction mechanism requirements. 1, the elementary steps must add together to give the overall reaction. And 2, the reaction mechanism must be consistent with the experimental rate law. Okay, we've talked about requirement 2. Requirement 1 is that all the steps in the mechanism must add up to give the overall reaction. So if we look at our mechanism, A yields C, C plus A yields B, we add those two together, the C cancels out, the A adds together, so we have 2A yields B. Yes, it's consistent with our overall mechanism. So here's another example. We have 2A plus B yielding C. That's our overall reaction. A possible mechanism is A plus B yielding D, and that we're told is the slow step. A plus D yields C, that's the fast step. So this is also a two-step mechanism. They can be longer than 2 steps. Okay, so what is D? D is an intermediate because it's formed and then it's used up. What is the rate law? So then we go to the slow step and we write it out from there. It would be rate equals K, A, B. That is, we see that A simply reacts with B. So we have K equals A to the first power times B to the first power. So it's first order with respect to A, first order with respect to B, second order overall. Here's another example. A plus B yields C plus D. That's the overall reaction. Let's say that we are told that it is second order with respect to A. So what that means is rate equals Ka squared. That's what we got from the experiment. So this means that 2 A's come together in the rate limiting, in the slow step. Here's a possible mechanism. A plus A yielding E plus C, that would be the slow step. The K1 over the yield sign means that's the rate constant for it. E is, of course, an intermediate because it doesn't appear in our overall reaction. The second step, the fast step, is E plus B forming A plus D. The 2 steps add together to give the overall reaction. So notice that the E cancels out, one of the A cancels out, so they add together to give the overall reaction, and the slow step is consistent with the rate law. Our next section is the collision model. Rate equals Ka to the n. So we've had that differential general generic rate law from early on in our chapter. K affects the reaction rate, as does the A concentration, as does N. We're focused on K in this model, collision model section. Experiments show that K increases exponentially with temperature. That means if we want to increase reaction rate, then we increase the temperature. K, it was found, K in general equals A times E to the minus EA over RT, where this is called the Arrhenius equation, and most rates obey this equation. Now, within our rate constant equation, A is not the A that represents the reactant. A is something altogether different. It is the orientation factor. Molecules must collide with the correct orientation to react. That is, if they need to collide head-on to react, as opposed to side by side, then they have to do that to react. A is the orientation factor. Again, it's not the A that describes the reactant. The E to the minus EA over RT part, that's the energy factor. It represents the fraction of collisions with sufficient energy to react. Alrighty, so we have what A is in our Arrhenius equation, and we have what E to the minus EA over RT represents. A little bit more on the energy factor. EA is what's called the activation energy. It is the minimum energy needed to break bonds and to rearrange atoms so they can react. Kind of like, think of making a campfire. You have to collect the fuel. Of course, oxygen is in air. But just because you have the 2 reactants, the fuel, the wood, and the oxygen, the fire doesn't just happen. You have to use a spark to make it happen. That's like this activation energy. It's overcoming this activation energy barrier. It allows the reactants to have enough energy to start colliding so that bonds can break and new bonds can start to form. So without this minimum energy, the reactants cannot react. This energy comes from the kinetic energy of the molecules, the reactants. It is transferred into potential energy and provides the energy needed to disrupt the molecules so they can react, allowing their bonds to start breaking so new ones can form. In our equation, R is the universal gas constant. We're here working with energy, so we have the value R equals 8.314 joules per mole Kelvin, and the temperature is Kelvin. A and EA are mostly independent of temperature. Remember from Chem 1, exothermic and endothermic reactions. Exothermic ones, the reactants are at higher energy than the products. So we would draw reactants are at higher energy than products. In an endothermic reaction, reactants are at lower energy than the products. Remember from Chem 1 that delta E or delta H represents the energy or enthalpy change between the reactants and the products. So that part is just the same as we had back in Chem 1. The new part here is that energy increase between reactants, what they have to go up to in order to then slide down to products. That's this EA. It's bigger usually in an exothermic reaction than in an endothermic one, because either way it has to be reactants up to the top of that energy barrier. Well, in an endothermic reaction, the reactants are at low energy, so usually EA is rather substantial, making those reactions typically slower. So now let's consider this reaction, 2Br-NO forming Br2 plus 2NO. It's an exothermic reaction, so draw the reaction profile. So it's going to look like what's shown there on the left. That is reactants at higher energy than products because it's exothermic, and then EA representing that energy barrier. Notice that in this case, the orientation of the initial linear molecule matters in order that Br2 can form. So it has to be that the Br atoms can get together to form. That's that part, that orientation factor part. So what Br-NO collision orientations can lead to a reaction? So we have that down here. For 2Br-NO to react, they have to collide with the correct orientation. And here are possible orientations. So A allows the BRs to be together. That can be a correct orientation. B also allows the BRs to get together. But C does not, because they're on opposite sides. Alrighty, back to the Arrhenius equation. So we have K equals A e to the minus EA over RT. If we want a linear version of it, we take the natural log of both sides and we get ln of K equals minus EA over R times 1 over T plus ln of A. If you match that up to a linear function, y equals mx plus b, you see that the y-intercept, b, equals ln of A, and the slope is minus EA over R. So here's a graph of ln of K versus 1 over T. It's linear with a slope of minus EA over R. And if we have a lot of rate constant versus time data, then for that reaction we can calculate the value of EA and A. So here's an example where we do that. We're given values of K in 1/seconds at many temperatures in Kelvin. For this reaction AA forming BB. When ln of K is graphed versus 1/T and fitted to a linear fit, the slope is -3010 K. What is EA? Alrighty, well, we have learned up here that the slope when ln of K versus 1/T is graphed, the slope is minus EA over R. So EA is minus MR. We have EA equals minus a negative 310 Kelvin times 8.314 joules per mole Kelvin. Kelvin cancels out and we get EA is 25,000 joules per mole or 25.0 kilojoules per mole. Here's a non-graphing example where we're given data at one temperature and we're asked to find the rate constant at a higher temperature. So we expect it to be larger at this higher temperature. So we have at 298 Kelvin, the rate constant for a reaction is 2000 seconds to the minus 1. The activation energy is 15.0 kilojoules per mole. What is the value of the rate constant at 348 Kelvin? Alrighty, so what we have is, from before, we have that A, the orientation factor, and EA, the activation energy, are temperature independent. So what we're going to do is we're given activation energy, but we're not given the value of the orientation factor A. So we're going to, first off, from our lower temperature data, we're going to find the value of A. So we take our Arrhenius equation, we rearrange it to solve for A, we put in our value for K, for EA, R, the temperature 298, we get that A is equal to 851,900 seconds to the minus 1. So now we go back to the Arrhenius equation and we put in that value of A, we put in the negative EA, the EA value 15,000. Notice we had to be consistent with units, we had to go from 15 kilojoules to 15,000 joules because of R having joules in it. So we put in EA, we put in R, we put in our higher temperature 348, and we find that yes, K does go up. It now has the value 4,800 seconds to the minus 1. All right, our last section is catalysts. Catalysts speed up a reaction by lowering the activation energy, by lowering that energy barrier. So a catalyst speeds up a reaction. A catalyst is used in the reaction and then is regenerated, so it's not used up. In our body, we have many catalysts, biological catalysts we call enzymes. And as we eat food, we need to digest it quickly so we get energy from it. Our enzymes make that happen. So an enzyme speeds up the reaction, but then is not used up. It's regenerated. And so that's part of the definition of a catalyst. Speeds up a reaction and is regenerated through the course of the reaction. Alrighty, so we see the energy versus reaction progress. This would be for an endothermic reaction. We see the energy barrier is substantially lowered from the purple to the blue one, being that there's a catalyst present. So in the purple one, we have it uncatalyzed, but in the blue one, it's the appropriate catalyst has been found, so the energy barrier is lower. And what that does is it increases the value of K and allows the reaction rate to be greater. So here's our last example, and we have not the overall reaction, we just have the mechanism for some kind of overall reaction. It's a two-step mechanism. The steps are A plus B yielding C plus D. Step 1. Step 2, C plus E yielding B plus D. So what's the overall reaction? Well, we see that the C cancels out and we see the B cancels out. So our overall reaction is A plus E yielding 2D. What is C? So C is formed in an upper step and then used up in a lower step. That makes C an intermediate. What is B? B, now that is what's new for us. B is the catalyst. It's needed in an upper reaction and it's regenerated in a lower reaction. That's part of the definition of a catalyst. So that makes it the catalyst. Alrighty, so this is then the end of chapter 12. We have gone through it quickly, so hopefully you will go back and listen to all or parts of this video, and you will get the handout and you will slowly at your pace go through all the examples, make sure that it makes sense to you. Definitely read chapter 12 in our textbook, do the assigned homework problems. That's it then.